link to the Zoom as well.
So are we going to have a mixed audience? I mean, Zoom and
yes.
YouTube and...
Yeah.
Okay, well
yeah, this is...
I don't know. Why do you need YouTube? Because there are not going to be that many people. So they could all join by Zoom, I guess.
Actually, we were like, for the next ones, we are expecting a lot of people. So,
hey, Anna. Hello.
We can hear you, Anna.
Let's see.
Yeah, probably you might see a lot of known faces, Mark.
Okay. Well, it would be nice if people turn their cameras on. It's much more fun to see faces rather than names, which I'm not even sure how to pronounce sometimes.
Paulo, do you want to make a kind of introduction about our idea of this series of talk?
Yes, let me... Mark, I will talk in Portuguese. I don't know how many people are connected, but...
Why will you talk in Portuguese? Because those people who don't understand English are not supposed to connect anyway.
Actually, yeah, but like students are connecting,
okay.
And they are like, they can understand what you are like technical things, but I think it's going to be easier even for me to explain our goal with this.
Okay, of course. Please speak whatever.
Okay, yeah. Just a second. Então, boa tarde a todos que estão conectados. Então, um grupo de estudos compostos por professores da Cruzeiro do Sul, tá? No caso, eu e a professora Ana Varela, da Universidade Cidade de São Paulo, no caso, a professora Sandra Freitas, e o professor Luiz Mochizuki, da Universidade de São Paulo, do campus da USP Leste. Nós estamos planejando uma série de seminários, e essa série de seminários pautados em controle motor e biomecânica, eles têm como objetivo introduzir ou fazer com que os pesquisadores do Brasil, eles conheçam o que os outros pesquisadores estão fazendo. E uma das formas que a gente encontrou para fazer esse tipo de comunicação entre pesquisadores do Brasil é por meio desse seminário que vai ocorrer provavelmente a cada 21 dias nesse semestre, e se nós obtivermos sucesso, nós pretendemos fazer isso a cada 15 dias. Tá? Então, esses seminários, eles têm uma característica similar aos seminários chamados de Action Club, que são ministrados na Penn State também a cada 15 dias. Tá? Então, um seminário ou algo mais informal, onde a gente tem um apresentador, e esse apresentador, no caso, tem 5 minutos, tá, de pausa, ou seja, ele pode fazer por 5 minutos uma apresentação, ele pode começar a apresentação, em 5 minutos esse apresentador, ele não vai ser interrompido, mas a partir dos 5 minutos, qualquer pessoa da audiência que tiver questões, pode levantar a mão e fazer questões para o apresentador. Tá? Então, é algo mais informal, mas creio que seja importante que todos nós, pesquisadores da área de comportamento motor no Brasil, a gente interaja mais, e essa é uma das maneiras que a gente pensou que seria interessante, principalmente nesse momento que nós estamos atravessando da pandemia. Então, nós vamos começar hoje com a apresentação do professor Mark Latash. Para muitos, o professor Mark Latash não precisa de introdução. Para outros, o professor Mark Latash é um dos principais nomes da área de controle motor no mundo, e ele tem vários livros publicados, centenas de artigos também publicados, e como ele é da Penn State, foi um dos criadores desse Action Club, nós pensamos que o melhor nome para estrear essa série de seminários seria o professor Mark Latash. Tá? Então eu vou ver se o Luiz, você quer dizer alguma coisa?
Eu acho que foi bem bacana o que você comentou, essa é a ideia. Né? E o Mark acabou sendo, ele é um inspirador para assim, né, particular para mim, para você e para a Sandra, né, porque a gente trabalhou junto na nossa pós-graduação com ele, né, e foi uma das coisas que a gente mais se divertiu no nosso tempo de Penn State é quando a gente assistia às sessões do Action Club. Né? Então, a gente quer criar essa dinâmica de discussão científica, né, entre os nossos grupos e entre as pessoas. Era isso. Thank you, Mark, for agreeing to stay with us.
Well, my pleasure, of course. So, should I take over?
Yes.
Yes, please.
Okay, thank you. All right, everybody. Thank you very much for joining. It's great to have another talk in Brazil, although I would certainly prefer to have it in Brazil rather than in a remote setting. But unfortunately, not everything happens according to our wishes. So I'm going to share my screen and then start with the talk. So, sorry, so messed up. We'll do that. All right. So, I selected a rather unusual topic for me for this talk, partly because of the Motor Control Summer School that was not that long ago when we discussed so many general issues related to motor control. So I decided to take a very specific phenomenon and then to try to unpack it and to see what's behind it and why do humans coactivate muscles. So, you know this example. So some people coactivate muscles to look more beautiful according to their own perception or to become governor of California. But we will try to stick to more or less scientific reasons. And rational reasons, more rational reasons why people coactivate muscles. So, as always, we start with definition. So, what is coactivation of muscles? This is simultaneous activation of muscles with opposing action. So, we sometimes call them agonists and antagonists for general purposes, but maybe flexor extensor, pronator, supinator, and so forth. These can be individual muscles, or it can be pretty large muscle groups. Sometimes they're called muscle synergies or muscle modes. For example, when people are standing, they may be co-contracting muscles of the ventral part of the body and of the dorsal part of the body simultaneously. So as a result, they kind of stiffen the whole body without moving it. So why would they do such things? Let me show you first a few examples of coactivation. It doesn't only happen in static conditions like you're standing. This is a very old illustration from one of the papers by Jerry Gottlieb, when the subject was asked to perform movements at different velocities. This is the agonist muscle. It's a flexion movement. And you can see the first agonist burst, the pause, and the second agonist burst, and the antagonist muscle, triceps. Well, we can see, particularly at fast speeds, at low speeds it's not that pronounced. There is not much activation of the antagonist seen. But at fast speeds we can see at least three components of coactivation. There is one at the beginning of the movement, which is simultaneous with the burst of the biceps, where the triceps is opposing the action of the biceps. So the task was to move as fast as possible. This doesn't seem reasonable because you're turning on a muscle that's acting against the required action. Then the so-called antagonist burst, that's more or less understandable because you have to break the movement, you have to decelerate it actively. And then there is a relatively long-lasting coactivation of agonist and antagonist muscle that can last for a few seconds. Also, it's not clear why people would do that. It doesn't only happen during movements, even more surprisingly, it happens in isometric conditions. So it's from the same group, but here is Dan Korkus, and this is one of the studies where he was the first author. When in isometric conditions, people were asked to do torque profiles from an initial 0 value to some target, again at different velocities. Take a look at the biceps and triceps EMGs. They're nearly symmetrical. So during movements, we can make arguments, oh, it's for stability, it's to make sure that the arm doesn't deviate much from the trajectory. Here, nothing moves. The arm doesn't have to be stabilized. Nevertheless, you can see huge amounts of coactivation of both muscles, both during the torque production and at the new steady state level. So we see coactivation that seems to be there without good mechanical reasons. But there are good mechanical reasons we can think of for it not to be there, because it's obviously wasteful if you want to make an action in a certain direction. Even higher coactivation or more frequent one is seen in people with unusual movements, with atypical movements. So you know that patients with any neurological disorders, when you ask them to stand, they would likely show very large coactivation patterns and coactivation of their leg and trunk muscles. If you perturb them, there will be huge co-contractions seen across all the joints along the body. Here is a situation of Down syndrome. In this particular example, the subject was sitting like I'm showing you now and was asked to either move the elbow quickly or to move the wrist quickly. When you do this type of movements, even if you move only one joint, the muscle activation patterns acting on both joints show very similar patterns. So on the left side, you can see typical triphasic pattern in the elbow muscles, biceps and triceps, and in the wrist muscles, wrist flex and wrist extensor. Both show typical triphasic patterns, so out of phase involvement of the agonist and antagonist muscle. Look at what happens in a person with Down syndrome, simultaneous activation of both muscles, both acting at the focal joint, the joint that was supposed to move, and at the joint that was not supposed to move when it is supposed to keep stable posture. So, preliminary conclusion from these first 7 minutes. Coactivation is a common phenomenon during movements by healthy people. Its magnitude increases with speed, but not only movement, but even in isometric conditions when it's torque production. It is increased across populations with suboptimal movements. And I didn't show you, but it's kind of obvious to everybody from everyday conditions. It increases in healthy persons in challenging conditions. So, for example, if you are standing on ice, or for the first time on roller skates, you will feel that all your muscles are co-contracting. Well, does it make sense? Well, let's consider first direct mechanical effects of coactivation.
Mark.
Yes.
You're talking about magnitude, but do you know something about the frequency components? If the frequency components are also in similar fashion, I mean, the spectrum of both muscles?
Well, the spectrum of EMGs during it is task dependent, but it's not much different. The spectral picture is not much different. The amount of coactivation in the antagonist is usually smaller than in the agonist. So the spectral picture may shift a little bit because of that. Like, for example, fewer motor units, fewer larger motor units will be involved in the antagonist than in the agonist, affecting the spectrum. But I don't think that there is anything special in the spectrum of coactivation as compared with spectrum of just activation.
Anna wants to ask something.
Yes, I have a question. What is the level of activation for each muscle that you consider as coactivation? Because
anything above 0.
Anything above 0?
Of course, you activate opposing muscle. Why do you do that? Even a little bit.
So you do not consider any noise or anything that is inherent to the system?
Well, no, noise is noise. We assume that our EMG system is good enough to distinguish noise from signal. But as you can see here, this is not noise.
Okay,
these are monstrous amounts of coactivation here. This is definitely not noise.
Yeah, but in this situation, you have a very well-controlled situation where probably you can control the degrees of freedom and everything. But let's suppose somebody's walking. It's really hard to control, and say, okay, anything above 0, it's signal, so you consider.
Let's not overcomplicate the question without a good reason as of now. So we're now talking about, say, single joint movement. And this single joint movement, like, for example, your knee movement during walking. If you want during walking, okay. And you will see coactivation at all times. Why? So that's the question. And I'm trying to offer answers. First, I'll offer you answers that are traditional. Like, you are increasing apparent stiffness of the effector, like, for example, of the joint. So when you're co-contracting muscles, you kind of stiffen the limb. Maybe it has reasons. Well, let's consider. So this is a single muscle. So this is force and length. And let's consider what defines the slope of the dependence between muscle force and muscle length. So when the muscle is relaxed, there is going to be a slight dependence of force on length due to the connective tissues, like tendon properties and other connective tissues properties. It's not controlled. It's just property of the peripheral part. Now, when the muscle becomes active when you stretch it, so its length is over the threshold for its stretch reflex. If the muscle is active, then the curve becomes much steeper. And the reflex contribution is very large, because if you take a diaphragmated muscle, then you will see this curve, which is shown here, which is not as steep as the muscle with reflexes. So muscle apparent stiffness is, by the way, I'm using the word apparent stiffness, not just stiffness, for a good reason. Stiffness is a very well-defined physical quantity that describes springs. Our muscles are not springs, but sometimes they behave in a way that they look like a spring. So I can measure something that looks like stiffness, but it's not. That's why I'm calling it apparent stiffness. All right. So the slope of this curve between force and length is the apparent stiffness, which is shown. So we have agonist muscle and antagonist muscle, which produces opposite torques in the joint. If we sum up these two lines, just point by point, we will get this line that's shown here with a thick line. This is the joint characteristic, which has a certain slope. If the muscles are perfectly symmetrical, as shown here, this characteristic is straight. Of course, our muscles are not perfectly symmetrical, so it's not always straight, but just for simplicity, it's not going to hurt the discussion by much. Let's consider it straight so that we can describe it with only one number, which is apparent stiffness of the joint. Note that this is controllable because, for example, if you shift these lines in such a way that they originate from the same point, that the stiffness will be very low. And if you spread them apart far away, this line will be very steep. So when you co-contract muscles, you effectively change the apparent stiffness of the joint. So why would you do that? Well, the first one, it helps move faster. That's true. Because if you have a spring-like system, and our muscles are kind of spring-like and joints are kind of spring-like, it cannot move faster than its natural frequency. Like if you can imagine, I have a spring and I take with my hand one end of the spring and there is an object that I want to move, and I move very, very fast. If I move too fast and the spring is compliant, I'll just extend the spring and the object will not move at all. Or it will move very, very slowly. If the spring is very rigid, the object will move immediately with the motion of my hand. So, natural frequency in a linear approximation is a square root of stiffness divided by mass. And of course, if you have higher stiffness, you have higher natural frequency, so you can move faster. So increasing muscle coactivation during movements is a good reason to move fast. Of course, not during isometric contraction, because nothing moves there. So it's a limited interpretation. We should also consider another thing. If you increase your stiffness, that comes with a price, because you are increasing natural frequency, but you are decreasing the damping ratio. And your system may become underdamped. And if it's too stiff, it can end up, after a movement, it can end up in an oscillation like that, which you probably would like to avoid. Effects on stability. Well, if I'm sitting and I'm coactivating muscles in my arm, my elbow joint becomes more stable, directly measured. You apply a perturbation and it doesn't move that much. If my arm is relaxed, it will move more with respect to the same perturbation. So in a way, the joint becomes more stable. However, that's not true when I am not sitting, but I am standing.
Calendário vai ficar todo marcado, o seu calendário meu também ficou todo marcado. E aí
what am I supposed to do? Hello?
Yeah, don't care.
All right. Will do my best.
Yeah.
Okay. However, if you are standing, if you don't have fixed origin, when I'm sitting in the chair, my trunk is immovable. I have a fixed origin of this kinematic chain of my arm. However, if I'm standing and I try to co-contract, this doesn't help. And by the way, because if I'm pushed and my feet are not glued to the floor, I will fall down, I will tip over. And people who do Tai Chi know this very well. They stay very relaxed and they're very stable. Their posture is very stable. So in our lab, we studied directly not that long ago effects of muscle co-contraction on stability of vertical posture. This was a study done some time ago by our visitor, Momoko Yamagata from Japan. We did the uncontrolled manifold-based analysis. Well, uncontrolled manifold was discussed several times during the motor control summer school. I'll just remind, it's a method of estimating stability by looking into the structure of inter-trial variance, so across multiple trials. So what you do, you select your set of variables, your space where you want to do analysis. In this case, these are muscle groups with parallel scaling of activation. We call them muscle modes. And then you select a variable, mechanical variable, that you think that the subject tries to keep stable. In this case, it was center of pressure coordinate. Reasonable. Then you quantify inter-trial variance in two components. One that doesn't change that variable, we call it within the uncontrolled manifold component. One that does, we call it orthogonal component. So when people were standing, our subjects, without coactivation, the UCM variance was somewhat higher than orthogonal variance. When they had high muscle co-contraction, purposeful, just by looking on the screen, it reversed, and orthogonal variance became higher than UCM variance. So this is poor stability. They lost stability by co-contracting muscles. We also estimated the same thing by measuring sway, components by postural sway. So we looked at center of pressure trajectory, rambling trajectory, and trembling trajectory. So two components of the sway. We looked at anterior-posterior direction and medial-lateral direction, and we simply quantified average speed. And it all increased with co-contraction. So when people co-contract muscles, they start to sway more, faster, and they show poor stability, a drop in stability. So co-contraction is not good for postural stability. However, patients do show co-contraction, and healthy people in conditions that are dangerous also show co-contraction. So why? So another group of preliminary conclusions. Coactivation is wasteful from the point of view of energetics and resultant forces and torques. It may be justified for very fast actions to increase the natural frequency of the effector. It does not help postural stability. Still, persons do it. Why? Well, to make sense, we have to switch from mechanics, because mechanics stops here. You will not make more sense. We have to go to motor control. So this my favorite picture of two frogs, that you have a living system and an inanimate system. So a real frog and a toy frog. And if you put them side by side, you step outside, you pour a glass of cachaça, you come back, you look at them, the live frog is gone, and the toy frog is waiting for you. Why? They're perfect copies of each other, except that one is live. You can actually have even another live frog and just spinalize it. Then they're really, really copies of each other. So why is the toy frog obeys laws of physics as we know them, and the live frog does something special? Well, we assume that it does so by using a special group of laws of nature that are based on basic physics, of course, but that allow the live animals to use different type of control to produce movements. In inanimate world, movements are produced by forces or changed by forces, and that's the only way you can do that. In animate world, in live world, movements are produced by changes in parameters of laws of nature. And I'm going to illustrate you what I mean. So here is the same picture, but even more simplified that I showed you before. Active muscle force as a function of muscle length. And let's forget about the small change in force due to passive properties of tissues. So this is the threshold of stretch reflex, and this is the characteristic of the muscle. We can write a simple equation. Force is 0 when our length is smaller than lambda, and force is some function of the difference between the two when our length is larger than lambda. All right? This is true for all skeletal muscles in our bodies, across all individuals, and even across species. So it's kind of a law of nature that's applicable to a very large group of objects. How do you move when you have this type of thing? So first of all, we can say that here, force and length are variables that describe these laws of nature. These are, if we consider only pseudostatic situations, these are the only two variables we care about when we think about muscles, mechanics of muscles. We care about its force and its length. Lambda is a parameter in this equation, which means that it doesn't obey to change if you change force or length. Like, for example, if you change length of muscle, force will change, not lambda. If you change force of the muscle, length will change, but not lambda. So lambda is free. It's not constrained by this law of nature. So how do you move in this situation? Well, that was suggested by equilibrium point hypothesis introduced by Anatol Feldman many, many years ago. So again, the same picture. This is your first value of lambda, and you were, for example, acting against a certain load, and you are in an equilibrium point, this equilibrium point 1. If you simply change the load, you will move to another equilibrium point. and this is passive movement. So if I'm sitting and I'm holding an object on my hand, a book, for example, and then I remove the book, the hand will move. So it's a passive movement. I am not actively producing it. It's produced by changes in external force field. Know that passive movements associated with changes in muscle activation, because muscle activation level, EMG, it is very low at the bottom of the curve, and it may be very high at the top of the curve. So it changes along this line. Okay? How do you do voluntary movements? You change lambda. You change it to a new value like this lambda 2. Now this equilibrium point disappears because this line doesn't exist anymore, and the system moves to the new equilibrium point, which corresponds to a new position of the muscle. So in both movements, passive and voluntary, you can see changes in force, in length, in muscle activation, in all three. It all depends on the external load. So living objects produce movements by changing in parameters of the laws of nature, and for one muscle, it is lambda. For a joint, there are two muscles at least acting against each other. So, for example, if they both initiate their active force production from the same point, your coactivation is 0. Then you have only one command that describes the system, which is the reciprocal command, or R command. So if you are here and you moved both characteristics to a new point, you will have a movement of your joint to a new position. If the two characteristics of the muscle have an overlap where both muscles are active, this is called the C command, or coactivation command. So for these two lines, which are shown with solid curves, the C command is relatively small. Here it is. And this is the joint characteristic. And if you shift them in opposite directions, the midpoint will remain the same. But the slope of the characteristic will change, and the C command is much larger. So note that both R command and C command are expressed in spatial units, not in newtons and not in units of stiffness, but they translate into changes either in position or in torque, depends on conditions, of course, or in stiffness, or in the apparent stiffness of the object that you are considering. According to this definition, coactivation can be negative, and that's very interesting. So there is no negative coactivation in physiology. The muscle can only have 0 activation, cannot have negative coactivation. However, coactivation command within this discussion, within this scheme, can turn from positive when there is a range where both muscles are active to negative when there is a range where both muscles are relaxed. And the midpoint of this range is still the R command. So these were defined, for example, R and C command were defined like R command is the midpoint between the two lambdas to the two muscles, and the C command is the difference between the two. But the difference can have positive sign or negative sign. And as we will see very soon, these have very strong implications for why people coactivate muscles. So we can now generalize the equilibrium point hypothesis. So we talked about muscles, then we talk about joints when there are at least two muscles, usually more. Usually we have a number of muscles crossing joints. And then at effector level, like for example, the limb or even the whole body. So how do you control such a system? You control at the effector level. So if I want to move a finger, I basically specify where I want it to be in space. The joints will have to obey because otherwise my body will fall apart. And then muscles will have to obey. So we have this mapping that looks like a redundant mapping, problem of motor redundancy. When we have reference coordinate for the effector level, for the endpoint, then we have to have those R and C commands for all the involved joints, and each joint is crossed by many muscles, so we have a lot of those lambdas at the level of individual muscles. How do we solve this problem, this apparent problem? Well, First of all, we have to reformulate it because it's not redundancy. We're using the word abundance, which has a different connotation because this means that you have many things, but you actually enjoy it. It's not a problem. It's a rich system that simply you have to learn how to use. So this is an illustration of a very classical paper by Bernstein, which was performed nearly 100 years ago when he asked professional blacksmith to produce repetitive working movements of the tip of their hammer to the object in their hand. And he recorded with his very old, strange system that he himself designed, he recorded the trajectories of the bulbs that he placed on different parts of the body. And then he looked across trials how repetitive the movements were. And he observed a very interesting thing, that the motion of the tip of the hammer was more reproducible than motion of individual joints. And the question is, how can it be? The brain cannot send signals to the hammer. It can only send signals to muscles. Muscles produce joint rotations. How come that the signals are highly variable that are sent by the brain that produce joint rotations, but the tip of the hammer that's seemingly outside the control of the brain is very reproducible? So that's where we get the principle of abundance, which suggests, coupled with the idea of control with reference coordinates, that you always start with specifying spatial reference coordinates for your important variables. That's your control. And lambda is a reference coordinate for a single muscle. Then you have these abundant transformations that are organized in such a way that at lower levels, like levels of commands to joints, there is a lot of variability allowed. You allow these variables to change as long as the variable at the task level stays more or less invariant. And the same when you go to muscles. So from trial to trial, there may be a lot of different lambda combinations used for this task, but they are confined primarily to a space where the reference coordinate for the task remains unchanged. So that's the uncontrolled manifold, that's the same expression. But now we translate the idea of uncontrolled manifold into the space of control variables. Now the only question is, how shall we measure it? Okay, we'll skip that.
Mark.
Let's consider...
Mark, back to the other slide. Do you think that if you think about biomechanical models and using some optimization method to calculate everything, do you think that thinking about this proposition, we should also think about every time that we look for a method to optimize the system, I have to think about the reference coordination as well?
I don't know why would one start thinking about optimization. Optimization is a tool from engineering. It's not from motor control. You can import this tool and start using it in motor control. It will give you some solutions, and most likely the solutions are not going to be very different from behavior, because our bodies do not violate any optimization principles by too much. So, but do they obey perfectly this principle? Of course not. This study already shows that there is no single optimal solution, even in the best trained subjects. These were professional blacksmiths. They trained this movement. This is their main labor movement. They performed it, 1,000 times for years, every day. If you have an optimal movement, they should have it. But they didn't show it. They showed a lot of variability in the joint level, in muscle activation level, obviously, which were compatible with the required trajectory of the tip of the hammer. So they did not optimize anything, or anything obvious at least. So I would say that optimality to me is a computational tool to describe something formally if you want to do that. But doesn't mean that it exists in the body. So these things exist in the body. By the way, I haven't yet offered you a single hypothesis. It's all reformulation of findings. like muscle characteristics, they are there. You can measure them in animals and humans. This has been done many times. Joint characteristics, same thing. You can measure them. So optimal things, I haven't seen a single person who was able to stick an electrode and measure anything optimal. So this is just a descriptive tool imported from another field.
Okay.
All right. So do people have these synergies? So we studied it in a very simplistic model, which is pressing with a single finger and producing a required level of force. At the level of mechanics, this is a non-redundant task. You have one effector and one task constraint. However, the level of control, it is an abundant task. So see, this is the coordinate of the effector, this 0, x0, and this is force. And here is your target, where you're supposed to be. Because you have agonist and antagonist muscles, you can change signals to these muscles to specify different referent coordinate of the fingertip, which is your R command or reciprocal command, and different apparent stiffness, which is your C command. Here I show you 3 examples how you can solve the same task within the accuracy constraints by using very different magnitudes of referent coordinate and very different coordinates of stiffness. Well, the force is, of course, your apparent stiffness, which is a function of C command, multiplied by the difference between these two. So our uncontrolled manifold is hyperbolic. It's a spring, if it's a spring-like system. So do people do that? Well, this is from our relatively old study. This is Satyam-Biquet who performed it. This is referent coordinate of the fingertip, and this is apparent stiffness of the fingertip. And these are a lot of trials, and the subject was asked to do it with different fingers, one at a time, or with all fingers together. It's all color-coded, but it doesn't matter. It's all then normalized so that we can plot all the data on one plot. So you can see that there is a very broad spectrum of these data points, but they are nicely confined to a hyperbolic line. If you do the hyperbolic regression, you will have a completely amazing R-squared value of very close to 1, like 0.99. So there are synergies, and they are very important synergies because people use them a lot. People use a lot of variability of their R command and of their C command, but they co-vary in a very nice way. They don't have to, by the way. This is choice by the controller. People don't have to do that. They could have selected a single point and just repeat it multiple times, but that's not how, like an optimal solution. From any optimization principle, you would expect, okay, there is an optimal solution. Why don't people simply repeat it again and again? No, they don't. They deviate quite dramatically. So, another preliminary conclusion. So I wanted, over the past 10 minutes, to tell you that there is a viable motor controls theory, the idea of control with reference spatial coordinates. It suggests that abundance at the level of control variables is actually used by healthy people to stabilize action. And loss of correlation of control variables may be associated with loss of stability and unintentional drifts in performance. I didn't show you those data, but if you ask people to perform this single finger force production task and remove visual feedback, the force will drift down. If you do this type of analysis of those data, you will see that the data points will not be very nicely aligned at the end of the trial with this line, not as well. So what does it mean for coactivation? Well, one more time. If you have your agonist lambda and antagonist lambda separated by a gap, your coactivation is negative. What does it mean? This means that, for example, if you want to produce different torques by the agonist, of course, the only variable that can produce changes in torque is lambda agonist. If you change your lambda antagonist, nothing will happen because it's beyond the the range with mechanical effectiveness. So in a way, your control becomes degenerate. You used to have two variables, lambda agonist and lambda antagonist, which translated into two commands, R command and C command. Now you have only one variable. So if you make a mistake, there is no way that you can use the antagonist muscle to help you correct this mistake. You lose synergies at the neural control level. By the way, if you change your antagonist lambda, your R formally changes and your C formally changes, but they have no effect on performance. They change in a covariant way that has no effect of performance. So you do not have synergies stabilizing action. I believe that this is the most important purpose of coactivation. Performance without coactivation does not allow stabilizing action at the level of neural control. As a result, you will become inaccurate and you will start to fall down and you will start to stumble and to start to mishold objects. You have to co-contract muscles. And you increase your coactivation if you perceive the task as challenging and unpredictable, because you want to have safety zone. You want to make sure that even if something moves, your antagonist muscle is still within the coactivation range. So you never go away from there, even in cases of unexpected motion. I believe that's the reason people co-contract muscles, not mechanics. Another reason to co-contract muscles, imagine that this is your muscle length where you are, and this is characteristic of your antagonist. In this case, it's very close. It's not coactivating, but it's very, very close. In this case, the muscle is really relaxed. Let's now keep in mind that shifts in your control variables in lambdas do not happen instantaneously. There is a limit to how fast you can shift them. For example, for elbow movements, we had independent estimates of the maximal shift of lambda. It's about 800 degrees per second. It's very high, of course. However, it's not infinite. So if you are 80 degrees away from your muscle length and you suddenly want to activate your muscle, it will take you 100 milliseconds extra to your reaction time. So another reason to coactivate muscles or to have your antagonists very close to coactivation is to reduce reaction time. So another set of preliminary conclusions. There may be several reasons for coactivation. Mechanical, it facilitates fast movements, but only for fast movements. For slow movements or for isometric conditions, it's not applicable. Control, it's always applicable. Ensuring abundance at the command level, at the neural control level, to stabilize performance. And that's what we always want to do, because without stability, no movement is useful. And psychology, to be ready to perform quick actions when needed, so to reduce reaction time. And just for your entertainment, I want to show you an example of our recent study related to coactivation, which was produced by a guy who just graduated from our group, Christian Quadra. What happens when people coactivate muscles while trying to produce constant force? So it's very easy to coactivate muscles while producing zero force. Just look at me, I'm holding my hand, and I co-contract all the muscles without moving the hand. It's very easy and natural to do. And so we asked our subject to do exactly the same way, but in a slightly different condition. We asked subjects to press on a force sensor like that, and then we told them, coactivate your muscles without changing force. That was the instruction. Coactivate your muscles without changing force. So what do you think the subjects would do? Well, in a way, if I ask 3 questions, I don't think that anybody except those who already heard these questions would be able to answer them correctly. So the 3 questions, experimental questions, were: what will happen with force with coactivation? Second question, what will subject tell you if you ask them verbally to report whether force went up or down, and by how much? And the third question, what will happen if you ask the subjects now to match it with a finger of the other hand? And let's imagine that the initial force is 10 units, whatever. So, okay? Try to guess. I give you 30 seconds, no less, because time is valuable. Try to think what will happen. Very few people can guess it right. So, let me start with this thing. If you coactivate muscles, you increase your C command. If you don't change your R command, the force should go up. Because, well, your system becomes stiffer, reference coordinate remains the same, you should see an increase in force. That's what the subject showed. They showed an increase in force, which was about 50% of the initial force level. What will they tell you? Well, here is what they did. So this is the initial target level. It's shown as target of this line. Left hand and right hand, no differences. The black line, immediately after coactivation, what they showed. The next gray bar, which is also increased, is a little bit later, but because we removed visual feedback, the force drifted down. I told you, without visual feedback drifted. It's still significantly higher than initial force. The white bar is their report. They say that the force dropped. The force went up by 50%, and they tell us that it dropped. And when we ask them to match, they overmatch. Or they say they produce forces that are at least as high, usually even a little bit higher. Isn't it amazing? So why? Okay, an increase in force we have just discussed. Okay. Why would they say that it dropped? Well, because their brain is a little bit smarter than them. So it knows that if you coactivate muscles, you have to start shifting your reference coordinate to avoid a large increase in force. This is in the right picture here. Reference coordinate 1 shifts to reference coordinate 2. This is now their force. A little bit lower, still increased. The open circle is the initial level. But a little bit lower. But their reference coordinate, look, it shifts towards 0. It decreased. So they confuse sense of force with sense of effort. And their sense of effort is the magnitude of reference coordinate. And they tell us that the force dropped because their reference coordinate shifted towards magnitudes corresponding to lower force. So they did not appreciate the increase in force. Well, they report lower force than the initial one. So, big mistake. Why did they match it correctly? That's a separate issue which would probably take me too much time to describe for you. It's actually related to the fact that to match force, even with the same effector, people, when they match force, they never match RC and they never match K. They, as I showed you in one of the previous slides, they are on that big uncontrolled manifold with a very wide spectrum of both. So when they ask to match force, they have to attend to force. They cannot match reference coordinate, or they cannot match K, because it's just beyond their abilities. So, and then they produce nearly accurate performance. So let's get to our ultimate conclusions.
Mark?
Yes.
So this is your interpretation of the data. So you didn't measure like RC and K.
We did. We did.
Okay. how
we
did you
measure RC and K, and it kind of fits this line.
Mm-hmm.
Yeah, of course we did, because we have this inverse piano, which kind of lifts your finger a little bit and lowers. And so you can measure the characteristic of the finger. And if you know this characteristic, you can interpolate it, and so the intercept will be reference coordinate, and the slope will be K.
And did you do the UCM analysis?
No, that would require too many trials. We didn't have, because we had so many conditions and trials in this experiment, we didn't have enough trials to do.
Do you think it's like doable and like it's something that you are thinking about doing?
We did a few studies now. I'm trying to remember whether we did UCM analysis. I think we did in a couple of recent studies, but I'm not 100% sure where they are now, because we have one good consequence of the fact that our lab has been closed is that we had plenty of time to work on the accumulated data. So we have now about half a dozen of papers that are under different stages of review in different journals over the past 3 months. And I don't remember now off the top of my head which ones of them have the UCM analysis. I think it's the paper, the better one is probably, I'm not 100% sure. It's a paper with force matching, which is in Press and Experimental Brain Research, but I think it's published already electronically. And the first author is Abolinch. He's a Latvian guy who's working with us. So ABO, Abolinch. So you can take a look. I think there is more stuff about it. We did not use verbal reports there, but we did use force matching and looked at RC and K in both task hand and matching hand, how they change.
Thank you.
Sure. All right, so ultimate conclusions. Coactivation should be analyzed at both peripheral level and, more importantly, at the control level. If you analyze it at only the peripheral, EMG or mechanical level, you can be misled, because EMG will never show you negative coactivation, but it exists. It's a true thing. Negative coactivation exists. Coactivation has purposes that go far beyond direct mechanical effects. For example, those mediated by increased apparent stiffness of the effector. It is related to stability, but not mechanical stability as affected by these changes in stiffness, but control level stability, when you can or you cannot co-vary your control variables to make sure that your performance is stable. And of course, motor control is fun. That's with respect to the last study. Okay, so I think we now have plenty of time for you to ask any questions you wish. This is, by the way, my lab currently. It's a bit of exaggeration, because like the 3 names of the students on the bottom, these are undergrad students who helped us during the spring semester. And during the summertime, 2 of them disappeared and they're not back yet, and I'm not sure if they will appear. Also, Christian Quadra defended and left us a week ago. Everything else seems to be in place. All others seem to be in place. So thank you very much, and ask your questions. If you have questions.
Hi. Hi, Professor Mark. Here is Maria Isabel.
Do you have a camera?
I do.
Oh, it will be much more fun to see you. Yeah.
Okay.
Hello. Well.
Yeah. Thank you for your talk. You said that mechanics is not the only thing that can explain coactivation. But I got a little interested when you said about perturbation. I was wondering how how inertia can relate to co-contraction when you increase velocity of movement. I mean, when you increase angular momentum, it gets more difficult to change it in a high amount. Like when you change the axis of rotation. So maybe I was thinking inertia can relate to that. Is that possible?
Well, mass is in both equations here.
Yeah.
So inertia is here, of course. Usually when we talk about coactivation, we do not consider changes in mass. Because usually but of course, if we consider different effectors, like a finger versus the whole arm or the whole body, the inertias are very different, and the K values should also be modulated appropriately, or as required by inertial properties. And we simply learn how to do it, I think. We get used to our own bodies, and we know its inertial properties, we know what to expect. What I never mentioned here, which is potentially important, is the fact that this B, this damping, damping goes hand in hand with stiffness, with apparent stiffness during co-contraction. So we actually have a very smart system. It knows that to speed up, we have to increase apparent stiffness. But then we can go into terminal oscillations, which the system wants to avoid. So usually K and B change in parallel with muscle co-contraction. So this is not a big issue. It is kind of an issue. It may turn into an issue if you, if you can imagine that you are co-contracting your muscles a lot and you are moving a very heavy object in hand, it will be very hard to stop.
Yes.
You may be able to produce a fast movement, but it will be very hard to stop because your damping is not going to be sufficient. So you'll have to learn how to do that with some kind of more sophisticated control.
And damping is related to any physiological property, or is it a system property in this case?
Well, system property comes from physiological properties. Yeah. It doesn't come from God. So, well, not in direct sense. So, of course, yes, it's all modular. Like all this language, the language of C command and R command, it's very physiological. Well, at least at the level of muscles and joints, where we know what to measure, more or less. Like at the system of the whole body, we don't really even know what to measure because there are so many objects, so many physiological mechanisms involved. But even in that case, there are quite a few studies that show, for example, that during standing, people do manipulate their R and C commands. We had, by the way, not that long ago, a study with one of your colleagues in Brazil, which describes how people produce whole body movement, like forward and backward, by changes in the R and C command. And Anatol Feldman, just a few months ago, published a paper with galvanic stimulation of the vestibular system that produces deviations of the body, showing that these deviations are actually deviations of R and C command. And the mechanics depends on the external condition. So it's not, stimulation of the vestibular system doesn't prescribe mechanics of the body or muscle activation. It prescribes changes in the R and C commands for the body. So it's all very, very physiological, I would say, as it should be.
Okay, thank you.
Sure. So, don't be scared. Ask questions.
Yeah. No more questions? Like, just turn on your microphone and ask questions. No questions?
I have a question, Mark.
Sure.
It's about Momoko's study. If you come back there, please, in the slide, I think we can see a large increase in trembling.
Actually, there is an increase in trembling and an increase in rambling. It's hard to say which one is bigger because statistically there is no interaction. I don't think there was an interaction, so we cannot really claim. But they are comparable. So if you compare this bar with this bar and then the bottom, this bar with that bar, maybe a little bit more in trembling. I mean, more likely what happened is that because trembling is kind of a more peripheral phenomenon, and rambling is a more brain-related, control-related phenomenon. So trembling likely increased because of pure mechanics, because of the fact that you increased apparent stiffness. Because if you increase apparent stiffness of your joints along the body, you will increase the natural frequency, and the system will move faster. However, as soon as it starts to move faster, you adjust your control, because otherwise, with your old method of control, the system may go out of control because it's too fast. So you have to adjust to that. So as a result, rambling also goes up its speed. Oh, I mean trembling and rambling also goes up.
Yeah, I was thinking, if you have a person, for example, Down syndrome, as you showed us, how could we reduce the coactivation in this population?
Why should we do that? I don't think coactivation is good. At least coactivation that seemed because coactivation allows them to make sure that they are in control of their action, that they can stabilize their action at all times. It may be energetically not very efficient, but energy is not a big limiting factor. Only if they want to do, I don't know, to run marathon, then energy becomes a limiting factor. But during everyday movements, it's not. So coactivating a little bit and spending a little bit more energy is okay if it contributes to stability of performance. So I will be very hesitant to try to train them to reduce coactivation. They may start dropping objects and falling if they learn to do it. So I think this is a learned good behavior, given the actual state of the body and of the central nervous system.
I see.
Mark, following this idea of coactivation is a good thing, do you think that coactivation should also appear in the anticipatory postural adjustments?
In conditions of predictable conditions and habitual normal conditions, no. And there is very little coactivation during anticipative postural adjustments. However, if you put people in in unpredictable conditions, we had a study not that long ago with Daniele Piscitelli, when we asked subjects to hold a load while standing and then to release it. They released the load by pressing a button. However, there were two loads, one in front of the body and one in the back through pulleys. So in some conditions, they knew which load would drop. And in other conditions, they didn't know. So one of the loads would drop, controlled by the experiment in a random fashion. So when they knew which load would drop, they showed very little coactivation during anticipatory postural adjustments. It was mostly reciprocal. If they did not know, they reduced the time of anticipatory postural adjustments and they started to coactivate muscles. So coactivation may be useful in healthy people as well. So like in that condition, because you don't know in what direction the load will drop, but you want your muscles to be ready to react in any direction. So it's not a bad idea to coactivate them. In a way, coactivation is not useful only in conditions when it is a strategy of desperation. I mean, you don't know how to solve the task, you start to co-contract muscles like crazy and you think that it would help, and it doesn't. But this is the only case when I think it's not useful. Otherwise, it's good to have coactivation.
Mark, but how much coactivation? Like, there is a range. Like, do you believe there is a range of coactivation? Like, there is an upper limit that if I go beyond this upper limit, I would have problems.
Well, of course, there is an upper limit of coactivation. Okay, let me just do this thing. All right. Of course, there is an upper limit of coactivation, which is simply related to our muscles' abilities to produce force. Mm-hmm. How much is optimal or good, I don't know. I think it's task-specific, person-specific, and how well trained you are to perform a task. So if you're doing a very habitual task in very habitual conditions, you don't expect any perturbations, stability is not a big issue. Well, you can have just a little bit of coactivation that you can ensure stability at control level, but you don't expect any troubles. If you expect problems, well, you have to increase coactivation to make sure that your stability control is better and it's very robust. So you never get to the picture that's shown now on the right side when the coactivation becomes negative, because then your stability is lost. Now, what's a good one? I don't know. I think as we saw, for example, in studies of Momoko with standing, the best results are with natural coactivation, which is pretty close to zero when people just stand quietly. The activation levels of the muscles is very small, and we specifically ask people to stand not vertically, because then you cannot record anything, but to stand a little bit inclined. Then you can record at least some muscles, some images, with visual control, of course, of their position on the monitor. Then you can see a little bit, but in normal conditions, there is very little coactivation in such tasks.
Mark, I have a question from Facebook. Sandra, she's asking you, can we think the atypical coactivation showed by special populations, for example, Parkinson, is only an access to control stability, not a compensatory pattern?
Compensatory for what? Because controlled stability is kind of compensatory. Because if they, since Parkinson's disease is associated with impaired stability. And well, there were quite a few studies, including those by Sandra and Paula, when they worked with us, when we quantified indices of stability, and they're reduced in Parkinson's patients. So it's quite possible that they see everyday tasks as more challenging than people without Parkinson's disease. So they would co-contract to make sure that they have enough room for ensuring stability, at least at a comfortable or acceptable level. So I'm not sure about the compensatory part of the question. So in that sense, yes, coactivation compensates for loss of stability. How efficient it is, I don't know, maybe not.
Mm-hmm.
Okay, let me check. Okay.
Okay. Anything else?
Yeah.
People like to hide behind the empty. Okay, let me stop sharing. Now, come on, guys. You should show me your faces. Okay, all right. Much better. Much better. Helpful.
Okay, Mark. So, alguém tem alguma outra questão? No?
Just one more.
Okay, go ahead.
So we can think, for example, we heard some elderly start to co-contract muscles. So we can think this as adjustment, that your physiology is changing, and so we can interpret like contraction is not help for stability when C goes near to negative value. Can
Yes.
we interpret like this? So
Yes.
we can judge co-contraction as being bad if C goes in a way that you compromise your stability. Not that co-contraction per se is bad, but a certain level is not good because it can compromise stability.
No, co-contraction by itself is not compromising stability by much. I mean, the mechanical effects are not very useful for stability. However, well, for stability of whole body tasks. For stability of tasks which you produce by an effector which is connected to an immovable system, co-contraction is good. It's mechanically efficient. But on top of that, I think what's more important, that co-contraction is useful to ensure stability of any action or any performance variable at the control level, because it allows you to use for any effector 2 variables per degree of freedom, which allows you to co-vary them to make sure that your performance is stable. Now, older people, I think that they simply perceive everyday tasks as more challenging, or typical tasks, or lab tasks, as more challenging than younger people. So they feel that they may need to react quickly, they may need to correct something more frequently than, for example, younger people. So they co-contract muscles more. They know, I think it's a learned strategy, because first time when you don't co-contract muscles and something bad happens, you fail, you make a mistake. And then you realize that it's better to co-contract muscles. So it's without understanding, of course, without explicit understanding of what's going on. It's just a learned strategy. I wonder whether it would be interesting to study whether there is a correlation between their subjective perception of how hard the task is and the amount of co-contraction they produce. And I would predict that people who think that the task is more difficult or more unpredictable, they would have higher co-contraction.
Yeah, there are studies showing that if you are afraid of falling, like if you have fear, like if you are in a beam, like 1 meter from the floor, and we stand on top of this, so you co-contract more. So
yes,
here you can voluntarily control the amount of co-contraction you do so.
Yeah, and the same happens, that's in the study that Luis Mochizuki did when he was in our lab, when we asked people to stand on boards which were fitted from the bottom with reduced surface area, with like a beam that could be narrow, but not dramatically narrow. I mean, it's much wider than typical postural sway amplitude. So if people did not know that there was a beam, they would stand quietly without any troubles. As soon as they got that beam and they knew that they were standing on a narrow surface, they all started to wobble and co-contract. Well, we didn't measure co-contraction, but I simply remember myself standing on that thing. Well, you start co-contracting muscles without even thinking what you are doing. And it doesn't help, of course. So the sway increases. So I think that at least part of the effects that were observed in Louis' study was due to the direct effects of muscle co-contraction.
Mark, there is another question in YouTube. It's written in Portuguese. Odair Baca. He's talking about people with stroke. And they say that in people with stroke, they have a lot of coactivation. And he's asking if coactivation is a kind of a compensation to improve stability, or a kind of deficit of reciprocal inhibition to relax the antagonist muscle.
That's a very good question. And the short answer is that I do not know. Reciprocal inhibition, I mean, the segmental reciprocal inhibition doesn't change that much. So, but there may be reciprocal relations among areas of the brain that suffer and that ultimately promote higher amount of co-contraction. In a way, I believe that these are not mutually exclusive things. Because if at the level of the brain, suddenly your reciprocal normal relations among neuronal populations that project on agonist and antagonist muscle, let's assume that they exist, which is questionable, then imagine that they become, as a result of stroke, lost. And then you're more likely to activate both groups of projecting neurons to the muscles simultaneously. But that's the same as increasing coactivation command. It's just different words, because inputs from the brain do not prescribe muscle activations. They prescribe lambdas or RNC commands. That has been shown already in quite a few experiments with TMS, with transcranial magnetic stimulation. So what you see in the periphery in the muscle is a reflection of both changes in the signals from the brain and maybe some peripheral consequences, movements or whatever happens during the measurement. So it's possible that in stroke there is an increase in the C command, which is forced by the stroke itself, which is not task specific. Then it's probably not very good, because you want your C command to be under your control and your R command to be under your control. Then you can use your coactivation or your non-zero C command to stabilize performance. If it's not under your control, it's already taken over by stroke, then it's of no use. How to distinguish between the two would be a very interesting question. I would actually be interested to run an experiment similar to what we've been doing to record the RNC commands in people after stroke and to see how much they're able to vary the coactivation command on their own, on purpose, kind of. rather than something that they cannot avoid, they cannot control. So good question. I don't have a good answer, but it opens. It's a question that can be studied experimentally, I believe.
Okay. Mark,
question?
Mark, can you hear me?
Yes, very well.
Marco here.
Yeah.
Hi, Mark.
Hi.
Does the contraction levels change depend on the learning of the task?
I would expect so, yeah. I think when you start a very unusual task, you would have an increased level of coactivation because you're not sure what will happen. Like people, when they start learning how to skate for the first time on ice, at first they co-contract like crazy and can barely move. Again, personal experience. When I was a kid and first time, I remember when I learned how to skate, it was awful at first. And then after some time, you suddenly realize that you know how to do it. And people start to, or a kid who is for the first time is put on the bicycle. They would be like that, co-contracting everything because they're afraid of falling down. And as a result, they will, of course, fall down because that's not very useful. So I would say that co-contraction is a natural kind of learned, or even evolutionary, I'm not sure, reaction to a dangerous, unlearned, unexpected situation. And as you learn it, the situation becomes more habitual, and then I would expect the level of co-contraction to drop. Probably an easy prediction.
Okay, thank you.
Sure.
Okay, we are 1:42, so I think it's time to end the session. First of all, I want to thank you, Mark, for your time, for this wonderful lecture. And I want to thank you all for participating in this seminar. And we believe that in 3 weeks we have another speaker, so we will advertise this talk again. And we hope that we can do something similar what's have been done at Penn State, so to have a regular schedule for talks about motor control and biomechanics. And nothing better to start with someone who is recognized as one of the most prominent name in motor control. So Mark, thanks again. And thank you all for staying with us up to this time.
Thank you very much. Nice seeing so many nice faces. I can even see Jose Barella, a piece of him.
Oh, yeah.
Hello. Okay, all right. Goodbye. Thank you all very much.
Thank you, Mark.
Thank you, Mark.
So in 3 weeks we'll be together again, and our invited speaker is Rogério Hirata. He's going to talk about movement and pain.
A gente pode falar em português, Luiz, então isso.
É verdade.
Então nós estamos só a gente. Então o próximo será o próximo palestrante. É o
Rogério Hirata, né? Rogério. Ele vai falar sobre movimento e dor, né? O Rogério é professor lá em Aalborg, né? E ele tem trabalhado bastante com dor, né? E ele é o nosso próximo convidado, né? Acho que à medida que as sessões forem acontecendo, as pessoas vão se relaxar mais e criar mais coragem para perguntar mais durante as falas, né? Para tornar bem divertida. Uma coisa que é curiosa, né, que isso, a gente aprendeu com o Mark esse tipo de palestra, né? E assim, quando o Mark organiza os Summer Schools, né, um critério dele de seleção, né, é escolher pessoas que não ficam chateadas quando as pessoas interrompem elas para falar, né? Porque tem gente que às vezes não gosta, né, quando você para a pessoa para ficar toda hora perguntando. Mas esse é o espírito que a gente quer, né, eu, Paulão, a Sandra, né, a Ana, que a gente quer criar de discussões, que isso é bem bacana. Né?
Então, a ideia é que pode interromper no meio da palestra, é isso?
Pode. Sim. Tá. Pode e deve.
Hoje a gente está dando um desconto porque foi em inglês, o pessoal fica meio tímido, né? Mas a gente vai ter que ter punição, Mochizuki, para quem não participa ativamente.
Sim. Mas foi bacana, eu achei bacana porque o Mark acabou falando de um assunto que ele não tinha comentado nada para a gente antes, pelo menos, né? Assim, é lógico que tem sempre conexão com as outras coisas que ele trabalha, mas foi um assunto bem interessante.
Sim.
Bem interessante. Bom, de qualquer forma, a apresentação está gravada, ela está no YouTube, né? Então quem quiser assistir depois está à vontade. Né? Usar em aula, essas coisas assim.
Tá joia, então. Então vamos encerrar por aqui. Quero agradecer a presença de todos e nos vemos daqui a 21 dias, no dia 3, né? 3 de setembro.
3 de setembro.
Abraço a todos e até mais, então.
Tchau. Abração, Paulão. Varelas,
pessoal.
Bel, Franklin, né? Marcela, Bruno,
gente.
Débora.
Vamos ver vocês.
Sim.
Tchau, Mochi, obrigado.
Jerônimo, tchau. Valeu aí, Edu. Ficou escondido o tempo inteiro, mas aí, Thiago também. Tchau, pessoal. Obrigado, Ricardo, também.